Guys, in this lecture, we're going to try to understand the relationship between what we're calling potential, or the voltage, and the work. Okay, before we do that, let's just do a little review of the relationships between electric field and potential. So I know that if I want to calculate the potential at a particular point, I can take this integral here to that point from infinity, or wherever I said that the potential, which is not a vector, is equal to 0. So I need that boundary value to actually do that. Okay, and that is a line integral. Okay, so we're integrating E dotted with dl, our path. In this case, this would be a situation where I know E. So for example, in that tutorial, which I literally just talked to you guys about, but probably happened a while ago for you, right? You found the electric field from Gauss's law, and then you used this equation to find V from the electric field. Okay, another way we can calculate the potential is through direct integration, and that's applying this formula here, okay, where I know the charge density, and I can draw a picture to figure out my separation vector, and I can integrate that charge over the sphere. Okay, in this case, that's a situation where maybe I don't know the electric field. I could calculate it, but I haven't done that yet. But I do know the charge density, and I want to find V directly from it. Okay, if I do it that way, I often do it that way because then I want to calculate the electric field by taking the gradient, the negative gradient of my potential. Okay, so this is a situation where if I know the potential, I can find or get the electric field. And then lastly, if I know, sorry, doing this wrong. If I know the potential, I can take what's called the Laplacian of the potential, and this is called Poisson's equation, and I can find the charge density directly from the potential. So I can get rho straight from my potential V. Okay, so if I look at all these relationships, it almost seems like a intermediary, kind of a mathy thing between our charge distribution and our electric field. In this lecture, I'm going to show you that it's more than that. It's more meaningful than that because it's related to the energy of a charge distribution. Okay, but hopefully this makes some sense to you right off the bat, because the one source of energy we're pretty familiar with are batteries, and batteries are classified or defined in terms of their voltage or potential, the amount of energy they store in the charge configuration that chemistry has provided inside the battery. So we're going to start this journey by remembering what the definition of work is in the physics sense, okay? So work, remember, is a scalar value that we can find by integrating the amount of force applied to an object, and that force has some component, which is why we have a dot product here, in the same direction as a displacement. So we're doing a force here times a length, but the dot product says, hey, if I've got some displacement here to the right, I only want the magnitude of, let me do that in a different color, of the force vector, if you can remember here, in the direction of the displacement. So that's why we have the dot product. Okay. And if we can remember with work, okay, work is related to energy, okay? In fact, we always say to have energy is to have the ability to do work. which means if I have energy, then I can exert a force on some object, have it cause a displacement, and potentially change the energy of that object, okay? So we have a equation for the electrical force that's given by Coulomb's law. And it's related to the electric field. I just have to multiply it by some test charge. Okay, so if I have some fully charged object, okay, that has some electric field, maybe not as uniform as what we're used to, but points in some direction here, okay. If I want to figure out how much work I need to do to take a charge out here from A, okay, and I want to move this charge all the way in closer to the field here to point B, then I can do the line integral. So I want to calculate the work to bring a charge Q from A to B. Okay, so that work is going to be equal to my electric force dotted with dl, but I actually need to add in a negative sign here because if I want to drag this charge in, okay, at a constant velocity, so this is the least amount of work I can do, then right, on one direction, it's feeling the electric force. I need to push that field in, I need to apply an equal and opposite force to push against that electrical force. Okay, so this force here, if I'm moving, say this is a positive charge, in the opposite, in the direction it doesn't want to go, right? It would rather flow away from this other flunky charged object because the way I've drawn the electric field lines, it's obvious that it's positive, but I'm going to push it in from A to B. That means I've got to, right, apply a force that's going to cancel out the force that the charge feels in the opposite direction, okay? So that's why there's that negative there, okay? Really let me write this a little bit clearer. I'm going to make this look like this is going to be F applied dot dl, and that F applied is the negative of the electric force dot dl. Okay, and then I can go a little bit further and I'm going to pull that negative sign out and a Q, and this is going to be equal to the electric field dotted with with my line. Okay, so this should look super familiar to you guys. We've done a lot on potential in the last week. This is how we defined our potential. In this case, it's going to be equal to the difference in potential at point B and point A. So now I've got that the work is equal to negative Q times the potential at B minus the potential at A. Okay, so now I have a direct relationship between work, which is the amount of energy, right, I need to transfer into this object to move it from A to B, being related to the change in potential of this object, okay? So I can generalize this and say if I move, say, my charge from infinity to some r, and I assume that for this charge distribution, it makes sense to say the potential at infinity is 0, then I can define or calculate the work just as Q times the potential at that particular value, the end value where I move the charge to. Okay, so in this case, let's say we've got some charge distribution and I'm moving Q here from infinity all the way into some R value. okay, where that would be the distance between maybe the center of my charge here and where my final point is. Electric potential is like a potential energy divided by Q. Okay, so let's make this analogy with gravity a little stronger. Okay, so for gravity, if I were to think about what I could make an analogous quantity for the gravitational field, this would be like dividing our gravitational potential energy, which is mgh, okay, by m. Okay, or I could make this a little bit more sophisticated, g little m over r. Doesn't really matter. The idea is still the same. The point is that you're removing the dependence of the mass in the field, okay? And here you're removing the dependence of the charge in the electric field. Okay, so for example, Ug over m, that being equal to negative g m over r, okay? I could say that this, what I'm just going to call a potential, but not a potential energy, it just depends on the position in the field, okay? Not on some object. So it's a little bit more general, a general way to define something that tells you something about how energy can be stored in that field. Okay, this potential that we can calculate with direct integration this way, okay, is also similar. That is a crazy R. Let me do a little better there. There we go. Okay, so this is analogous because this potential, okay, depends on E, not on the charge of an object. That being said, let me say potential does not, or potential, let me say it this way, it is not energy. Okay, units don't work. But when I multiply it by charge, or by the charge of the object whose energy is changing, or could change, you get a quantity that can be used to calculate the energy stored, okay, just like potential energy. And in that way, you can think about if I release a charge that has some of that stored energy, that potential energy will be converted back to kinetic energy. Okay, so let's go back here and think about this picture. Okay, I calculated the work I needed to do to move A all the way to B. That work was storing some energy in this particular charge configuration. It's like compressing a spring, right? When I bring this Q into point B closer than it wants to be. When I let go of this charge, if it's free to move, it's that energy that was stored is going to be released in terms of kinetic energy as it moves away from this charged object, which is to say, if I measure the energy that it has back at A, right, it's accelerated this whole time. So if it started at rest at A and then I pushed it in, it's not going to be at rest when it gets to A again if I let it flow back out. The amount of energy that it's going to have at A is going to be equal to the amount of work I did when I pushed it into B. Let's think about the work done along a closed path. Okay, so if I want to calculate the work done along a closed path, I'm going to do the same thing. Okay, so I could think about going from A to B, maybe along this path here, and then I'm going to come back, have more fun, and I'm going to go back along path 2. If I wanted to calculate the total work, I would have to split this integral up into 2 chunks. The first chunk would be this first path when I started at A and I went to B. Okay, and that would be the electric field along that path, dot dl. And then the work along 2 would be, again, opposite direction from A to B. Again, I would be dotting that along the dl, okay? But we know, for example, we know that the curl of E is 0. Okay, that also means that if I were to integrate the electric field along a closed path, it has to be equal to 0. Okay, we can also think about that in terms of the curl being equal to 0. That's how we define the curl. Okay, so I know that the work done along path 2 has to be equal to the negative work done along path 3. Okay, this is to say, this is what is true when you have a conservative force. So again, gravity is another conservative force. Okay, that means work does not depend on the path. And if it doesn't depend on the path, that means that the energy that is stored or loaded into a system when you do work is conserved. Okay. It can be reclaimed. It's not lost to dissipative forces, right? Like friction, the energy is lost to thermal energy or heat. Okay, so that should make sense again. If I'm going to move this object from A to B, it shouldn't matter what path I take. I'm still going to load this system, which is Q and my funky charge object, with the same amount of energy. Okay, I just want to make one more analogy between potential and gravity, okay? And that's just some practical thinking about how charges move in a field. I want you guys to note or recall that positive charges are going to move from high potential to low potential. So you can think about that as them going downhill, okay? So that's analogous for gravity. Here, gravity, if you think about what we called potential, so this is just a mass. So it also naturally flows downhill. Of course, negative charges, it gets a little confusing here. They naturally go uphill. We don't have anything like that for mass. Okay, but that's a similarity. Okay, and then again, like height, we can set V equal to 0 anywhere. Okay, it's arbitrary. Okay, so in summary, I want you to think of potential kind of like height in a gravitational field, and I want you to think about Q times the potential as kind of being like gravitational potential energy. Okay, that's the similarity that we're looking for in this analogy.